Okay, hello class. This is a video on assignment number 9. Okay, so I'll give you some detailed information on the last assignments. Remember, this assignment is part of the final exam content, and so I do hope you practice each one of the questions here. Okay, yeah. So first question. There are three questions basically, and this is essentially evaluation of a surface integral or calculating the flux through a certain surface. So what you need to do is you have the formula sheets. Okay, the formula sheet provided the formulas for a surface integral. Essentially, you need to identify which case you are dealing with, and then you choose the formula properly at here. Okay, yeah. Okay, so let's take a look at this question in here. Yeah, part A. This is a vector field, and the surface is a sphere, and the direction is outward to the surface. So basically, the last sentence at here determines how would you choose that n hat. All right, so this is a surface at here with a radius of 3, right? So according to the formula, the n hat is 1 over 3. That's your radius x, y, z. Okay, and your dA is a at here is 3. So sorry, a squared. Let's look at the formula right here. Okay. A squared sine phi d theta. Okay, so a squared is just 9 sine phi d theta. Okay, so it's dA. And remember, okay, you need to basically replace the x, y, z, right, with x equal to a times, so 3 times sine phi cosine theta, and y equal to 3 sine phi sine theta, and z equal to 3 cosine phi. Okay, so this is the x, y, z that you're going to replace. Now we're ready to evaluate this surface integral. Okay, so f x y z n hat is 1/3 x, y, z, and dA is this guy here, so 9 sine phi d phi d theta. Okay, so this dot this, you get 1/3 x squared plus y squared plus z squared, and 9 sine phi d phi d theta. So if you plug this x, y, z into here, you actually end up with basically the sphere equal to 9. So this guy here, right, equal to 9 if you plug this x, y, z into here. So what we really end up with is 1/3 times 9 times 9 again, sine phi d theta. Okay, so now figure out the limits for phi and theta. If you draw here, so this is a phi, right? Yeah. So basically phi, you rotate this starting from 0 up to the bottom here, so 0 to pi, and theta, it will be 0 to 2 pi. There we go, right? And then plug this. This is 27. So it's pretty simple integral, okay, equal to this. So part B, okay, do the same thing, but the surface is rectangular surface, y equal to 0, and x is between this range and z between this range. Direction negative j hat. So this is basically the plane, right? This case here. Now in the formula, the plane is z equal to a, so that in that question it's a bit of different from this plane here, right? but you can easily make a little bit adjustments at here, so to match this part B, this question. So what we're dealing with, the surface is y equal to 0. So y equal to 0, basically, which is what? Which is this xz surface here, and x between -1 to 2. So -1 in here, 2 is here, so -1 to 2, and z is between 2 and 7. So this is 2 to 7. So what are we dealing with here? So we're actually dealing with a rectangle, okay, something like this, right? Okay, so in this case here, the direction for n hat, right, it's already given, some negative g hat. So basically this is n hat direction, and dA, when you pick a section here, dA is the dx dz. Okay. So then the surface integral will be okay, so f dot n hat dA, okay, and f is yx squared minus -2 and xz, okay, and dot this n hat is 0, -1, 0, dA's dx dz. Okay, yeah. So plug it in. Okay, so this dotted out here. Okay, remember the y actually is 0, so remember this is y equal to 0. That's the plane, right? So you really simplify. This really doesn't matter, because when you this times this is already 0. So -2, this is 2. This times 0 is 0. So 2 dx dz. X limit is between -1 to 2. Z is between 2 to 7. Okay. Yeah. Well, this is equal to 30. Okay. Part C. See what's the surface for part C. So the surface for part C is z equal to x squared plus y squared, and z is between 0 and 1. So this is a paraboloid. So this is actually which case now? This is a case number 4. This is general surface. So this one here. So we should use this surface right here. Okay, yeah. So if I use that surface, so n hat dA, according to that formula, which, okay, first of all, for this one here, the direction, right? Direction is upwards. So if it's upwards, so we're gonna pick the positive, basically, positive right here. Okay, so not a negative one, positive this guy here. So then negative fx, negative fy, 1, and dx dy. So this is a function, function f, which is x squared plus y squared. So partial derivative, negative 2x, negative 2y, 1, and dx dy. Okay, so then the surface integral is f dot n hat dA. Okay, what is f? F is 4x, 4y, and 2 dot this guy here. Okay, yeah. Okay, so carry out this dot product. So this times this plus this times this plus this times this, we are getting negative ax squared minus ay squared plus 2 dx dy. Okay, so x and y limits are determined by the shadow, okay, of the surface in xy plane. And here's a paraboloid, right? Here's a paraboloid, and the top is 1, so the shadow is basically a circle, right? And so the shadow is at x squared equal to y squared equal to 1. So this is the shadow. Now, if this is a shadow, so when we integrate based on x, y limits, and it's a circle, so we actually might as well use polar coordinates at here, right? From here. So using polar coordinate, which basically means x equal to r, which r is 1, so x times 1 times cosine theta, and y equal to sine theta. Okay, so and then dx dy will become r dr d theta. Okay, so if you plug it this is r here. Yeah. X equals r cosine theta, y equals r sine theta. So plug this into here. Here you get negative 8 r squared plus 2, and then r dr d theta. The limits for r, this is a shadow at here. It's from 0 to 1, and theta is 0 to 2 pi. Right, it's pretty straightforward. So this is a simple integral here, so you get negative 2 pi. Okay, so these three questions in here essentially is a practice of the surface integral or calculation of the flux. Okay, yeah. So let's look at the second question in here. Okay. This one is a little bit tricky, and this is basically calculating application of divergence theorem. Okay, so I'll just copy the question in here. Okay, let's look at this question and then see what we can do at here. Okay, first of all, okay, understand what we're dealing with here. This is basically an object enclosed by two surfaces. One is the green part of the surface, which is this sphere, okay, spherical surface, and then internal there is a cylindrical surface, okay, which is drilled right through the center of this sphere. It's basically an apple, eaten right through the center of the apple here, right? And then this is the region D we're dealing with. Okay. So the first part of the question, okay, so in the question S, right, it says the S is the spherical surface, and then there is this internal cylindrical surface here, right? Now, yeah, the sphere has a radius of 2, and the cylinder here has a radius 1. So the first question is, given this vector field, let's calculate the flux outward through the S. So what we need to look at is what's the outward flux, right, out of this this outside surface here. Not necessarily this vector F, you can draw it properly here. And then the second part of the question is to show that the flux of this vector through the cylinder, doesn't matter whether it's this way or that way, you want to show the flux through this cylindrical surface is 0. Okay? Yeah. And then we'll look at the part C. So let's look at the part A. Part A again, it is a surface integral exercise, okay? But it does specifically say it's the flux outward through this S. So that keywords will give us this n hat. So n hat is 1 over a x, y, z. And a is, in this case, 2. So x, y, z at here. Okay. So let's use the formula for using spherical coordinate, because this is a sphere, right, centered at the origin. So I'm going to use n1. Okay, so basically this is the n1 is the uninormal vector, okay, outward to surface S. Okay, so because we're going to deal with this cylindrical, I use n2 for that one there. Okay, and dA, okay, is 4 times sine phi, okay, which is basically a square, okay, times sine phi times d phi d theta. Okay. Okay, so let's see. Now what do we do? It's surface integral, so S, f vector dot n hat dA, okay, and f vector is y negative x z, okay, dot 1/2 x y z n hat in 1 hat, okay, and then dA is 4 times sine phi and d phi d theta. Okay, this is S here. So calculating the dot product, so what we're gonna get Okay, so 1/2 is x times y, negative x times y, so it's cancelled. Then there's z squared, so 1/2 cancel 2, so there's 2z squared sine phi d phi d theta. Okay, and z squared, right? You know, you need to replace the z with what? A times cosine phi, which is 2 times cosine phi. Okay, so basically this surface integral becomes 2 times sine 2 times 2 cosine phi squared sine phi and d phi d theta, and that equal to 2 times 4 is 8 cosine phi squared sine phi d phi d theta. So the limits for phi, this is a bit tricky. So the limits of the phi, right, is the phi angle corresponding to the surface S, which is the black part. Okay, you know, the gray part, this part. So when you draw the line and here, this is the line, this is the edge corresponding to this surface S, and that's the other edge. So phi angle is defined between the z-axis and this reading line here. So this would be phi mean, and then from here to here will be the phi max, right? So this is a phi mean, and then this is the phi max. Okay, yeah. So how do we figure out the exact value of phi mean and phi max then? So we use the geometry at here. So remember, the radius of the sphere is 2. So from here to here is 2 here. Okay, well, here to here is 2. And radius of the cylinder is 1. So from here to here is 1. So we look at this triangle here. So this is 2. This is 1. And use your geometry here. So cosine this theta is equal to, or it doesn't matter, if this is phi at here, right? This is phi mean. Okay, this is phi mean, or this is phi mean. It's the same thing. Yeah. So basically, say sine phi mean equal to 1 over 2, which means the phi mean is pi over 6. Okay. So if this is pi over 6, it's symmetric, and then this is also pi over 6. So pi minus pi over 6, you know, from here to here, right? So phi max is pi minus pi over 6, which is phi over 6. There we go. So my limits for phi is pi over 6, okay, to 5 pi over 6. And theta, right, you know, in order to sweep, basically you need to sweep 360 degrees here, right, because of this region is 360 degrees here. So this is 0 to 2 pi. Okay, so that's the setup for this double integral right here. Okay. Okay, so the rest of the work is just integral now. You probably have to use a substitution rule right here. Yeah. Basically, sine phi, this is d cosine phi negative, right? Yeah. So you put a negative right here. Okay. Yeah. Then the rest of the work, okay, then you can figure it out. So this should be give us this 4 root 3 times pi. Okay, so that's part A. So part C, as part B, okay, part B is want you to prove the flux through this cylindrical surface is 0, whether it's inward or whether this direction or that direction, right? So let's take a look at this, how we can quickly prove this one here. So the essence of this flux, right, is F dot n hat. So let's say call this n2 hat, right? This is the direction n2 hat, or the other way, doesn't matter. So f, right? Let's see, what's f? We already have the f, and that's y, negative x, and z. And this n2 hat, this is the direction. Maybe this is n2 hat. Let's see, let me change it the other way here. Okay, yeah. So the n2 hat is because it's cylindrical surface here. So use the formula sheet. Okay, n2 hat is this is 1 over a x y 0. Okay, so which means this is 1 over a, but the cylinder is 1, the a is 1, and then x y 0. Okay, so this dot this, let's say this dot this, what is it equal to? F dot n2 hat. So this times this plus this times this plus this 0, so it is 0, right? So which basically means the dot product, this dot product is 0, and which basically means what? This means this surface integral here will be always 0. The flux is 0. So I should use a different, probably use a different surface here. This is called cylinder here. Okay, yeah, because not S anymore. The S here in the previous one, the symbol S referred to the spherical surface. So that's the last case here, part C. Okay, part C, you got to interpret it a little bit careful at here. Okay, so part C asking is use divergence theorem applied to this vector field. Okay, and compute the volume of the region of this solid, basically between this cylindrical surface and a spherical surface, okay, or the apple. So usually, when you ask for calculating volume, you're gonna do a triple integral, basically d and dv. This is the volume, right? This is volume here, and you can actually calculate this volume using the traditional methods as we learned in triple integral. And I think you can use spherical coordinates. Basically draw a reading lines out of this region, get rho mean, rho max, and then find the limits, right, for phi and theta. Then you can calculate this volume here. But over here, I don't think it's going to ask you to use the traditional method. Just apply the divergence theorem here. So let's see, right? What is divergence theorem first? You have the formula in the formula sheets. So if you ask you to use divergence theorem, then you're gonna have to use the divergence theorem. This is divergence theorem, right? Yeah. Okay. So one side is triple integral, and the other side is a double integral. So as it says, right, divergence theorem, the capital D, which is region D, is the region enclosed by the surface S. If surface S consists of multiple surfaces, let's say S1 and S2, then you basically do this. Okay, yeah. So in this case, this is exactly the case at here. So you look at the surface, the region D, which is this region at here. It is enclosed by two surfaces. One is this spherical surface, and the other is this cylinder surface at here, right? Yeah. Okay. So first of all, if I use divergence theorem, it's divf, okay, and dv, okay, this is the formula, okay, and that equal to, for there are two surfaces, right, equal to the two surfaces. One is a sphere, f dot n1 hat dA, and there's another one, there's a cylinder, f dot n2 hat dA. Okay, yeah. So in both cases, this n1, this n2, if you remember, right, n1 hat and n2 hat, they're going to be the outwards, okay, the outward direction, okay, outward directions. So we don't really have to use this, but just kind of emphasize it here. Let's see. For the sphere, this is n1 hat is outward, but for the cylinder, right, what's outward? This is outward, n2 hat, not the other way. Okay, because you look at this one here. So this is n2 hat, right? This is out of this outwards to this region D at here. But anyway, so let's calculate it, right? Let's look at what's divf at here, which is del dot f. Okay, f is this this is a vector field at here, and that equal to partial x, partial y, partial z. Okay, dot y negative x z. Okay, so calculate this. So partial x over y is 0, partial y over x is 0, partial z over z is 1. So this divergence of this vector field is 1. So when you put the 1 over here, note of that this triple integral is actually the volume. So that's why the question is asking you to do this, right? Asking you to evaluate this volume, right? Now really evaluating this volume here using the divergence theorem. So you try to obtain this and that. So adding this together, that gives you the volume over here in this case. Okay, yeah. This is just a coincidence. Okay, first of all, not all del dot f will be 1, right? Because in this case this is 1, so you can actually calculate this divergence, right? Using the other side, which is the surface integral. Okay. Now, if I look at these two at here, right? Look at these two surface integral. We actually already calculated this first surface integral in the part A, right? This is the value in the part A here, and this surface integral you can calculate in the part B, which is a 0. So basically, the volume is this guy here. Okay, yeah. So it's pretty straightforward, right? And it's simple. So if you calculate using traditional method, you will be able to get the same answer though, right? Maybe I can try, just not really confuse you here. If I wanted to use a traditional method, let's see, right? What would be your limits, okay, for traditional methods? Okay, if you use a traditional method, you're gonna draw an arrow line out of here. So this is rho mean and rho max, right? Rho mean, rho max. So and this will be the phi angle, okay, from here to here, the phi angle, right? And this part here is 1, okay, this part here. Okay, this part is 1 here. So rho mean, you draw here, this is basically 1 in here, okay. And this is phi at here. This is rho mean. So rho mean equal to, what is it equal to? So sine phi equal to 1 over, so 1 over sine phi, right? 1 over sine phi. Okay, so if I need to use traditional triple integral, so calculate the volume, 3 and here. So dV is rho square sine phi d phi, sorry, d rho d phi d theta. So rho, as we just said, rho mean is 1 over sine phi. So that's rho mean, right? This rho mean. Second contact, rho max, which is 2. Phi angle, that's the same phi angle as we can find it out. So phi, this is phi mean right here. This is phi mean and phi max, as we figured out, 6 pi over 6 to 5 pi over 6. And theta will be 0 to 2 pi. So this will be the setup for traditional, right? And you can calculate this this integral here. Okay, so that's second question. Let's move on here to third question. Okay, so another question that you can use divergence theorem. Alright, so let's read the question here. Here's a vector field. Here you have a surface S, which is this, okay? Not a spherical surface. This is a paraboloid, inverted bowl, okay? This is not a sphere, okay, or not part of the spherical surface. Okay, yeah. Now, what do we need to calculate? We need to calculate the flux across this surface S and taking upward direction, no, upward flux. Okay. And then, okay, I ask you to do two different ways. One is directly calculate using surface integral, and the other one is use divergence theorem again. Alright? Yeah. Okay, good. So let's look at this part A at here. Okay. Okay, so traditional methods, I think we are pretty comfortable now. So you need to identify what kind of surface you're dealing with. I said it's not a spherical surface. This is actually explicit surface. This is z equal to f of x, y. Right? So we choose n hat dA. And because we need upward calculation, so we choose this n hat dA at here. Okay, yeah. This is function f, so partial f over x is negative 2x. So negative negative becomes positive. Same thing for this 2y, and dA. Put dx dy in here. Okay, yeah. So dx dy is determined by the shadow, which is the circle, right? Which is circle. So when you set z equal to 0, and this is basically 1 equal to x squared plus y squared, unit circle. Okay. Yeah. Okay, so try to evaluate the surface integral, and f function is x, y, 2 times y minus z. Okay, this is a vector field f dot n hat dA, 2x, 2y, 1, dx, dy. So this times this, plus this times this, plus this times this. So 2x squared plus 2y squared plus 2y minus z. Okay, dx, dy. Okay, so there's a mixture of x and y at here. But we only deal with x and y, so we remember this is surface integral over this surface defined by this function z equal to y minus x squared minus y squared. So we need to replace this z with the actual surface function. One minus this guy here. So 1 minus, okay, let's bracket. Okay, so expand it. So this y minus 1 is gone, minus minus becomes positive, so 2x squared, 2y squared. So you actually end up with 4x squared plus 4y squared dx dy. And the x and y is determined by the shadow at here, which is a circle. So then we switch to polar coordinates at here. So replace x with r cos theta, y equal to r sin theta. We got 4r squared, then r dr d theta for dx dy. R will be 0 to 1, and theta will be 0 to 2 pi. Okay. So this will be 2 pi. So that is a traditional calculation of the upward or outward, flux for this surface S at here. Second part, instead of calculating this surface integral, it wants to use divergence theorem So you need to look at this basically into this guy here before you can appreciate why you use divergence theorem here. Then again, what we choose is, we can choose this as region D. So look at this region D here. So region D is enclosed by two surfaces. One is this parabolic surface, and bottom this disk right here. So let's call this bottom surface T. Okay, the disk T here. So D is enclosed by this. Then according to the divergence theorem, if you're going to calculate this DIF dV, okay, this is the divergence theorem, one side triple integral, right? Then what is it equal to for the other side? Is equal, because it has two surfaces, so it's actually equal to the S plus T, these two surfaces, right? And F dot N hat dA. Okay, yeah. So this is a divergence theorem here, right? Yeah. And N hat, remember this is the outward direction. So then again, let's calculate DIVF, which is del dot F. Okay, yeah. F, this is F function right here. So if you calculate, okay, partial over partial x, partial over partial y, partial over partial z, dot, okay, x, y to y minus z. Okay. So what do we get? Partial this over partial x is 1. Partial this over partial y is 1. Partial this over partial z is what? Negative 2. Right? Negative 2. So 1 plus 1 minus 2 is 0. So this divergence 0. Then this side, the triple integral, it will be 0. Okay? So this would be a big 0 in here. If this is a big 0, and there are two surfaces here, so we get this is S and T, right? Yeah, surface integral. So this plus this equal to 0, which means what? Which means this surface integral will be equal to the negative that surface integral. Okay, yeah. And this is idea of this part B, asking you to use divergence theorem to calculate this surface. So we calculate this in part A, right? In part A. But I don't, the part B is, it doesn't ask you to calculate this again. It asks you actually basically calculate this guy to get the value of this, right? See if that can actually make it simple here. So remember, this T is the surface of this disk at here. Then this n hat is normal, but this n hat comes from the divergence theorem. So this n hat, right, according to divergence theorem, this n hat needs to be uninormal vector outwards of this surface here. So look at this. If you look at this, this one here. So for S, this is outward. Okay, let's say this is n1. Then for the T, the outward is what? It's down, right? It's down here. So basically, the n hat, okay, that's called n2, is basically negative k hat. Okay, that's your n hat, right? This is going down in here. Okay, so then let's see, is that going to be simple? So T is basically a plane here. If we're gonna use formula, so we're gonna choose basically this part of the formula, right? Yeah, this part of formula. So let me calculate this guy here, negative. So F is x, y, 2 minus z. And n hat, right? Remember, n hat is negative k hat. Okay, so n hat will be 0, 0, negative. dA, and will be dx, dy. Okay, so this is 0, 0 has to cancel this out, this x and y. And the y, the negative 1, right, times this is 2 y minus z. Okay, dx, dy. Now there's a z at here. Then what is the z value then? Right now your surface is this disk inside this xy plane. So the z value is naturally be 0. So then we replace the z with 0, right? Then your total integral right here is 2 times dx dy. Okay, so 2 is constant, so take it out. So negative 2, okay, and dx dy. Okay, yeah. And this portion right here, right? This portion here is basically the area, right? The area of this this region, this surface T, which is a disk, which is a unit circle. So area is unit circle, pi r squared is pi, so negative 2 pi, right? So negative. Just a second here. Sorry, I missed them. So it's 2 times this is negative. Okay, there's a mistake. There's 2 times there's negative, and the negative and negative cancel out. So this is not negative anymore. It's negative. So negatives here. So 2 pi. So basically, so this surface integral of 2 pi, and that's the same answer as part A, right? Yeah. Okay, so this is problem number 3, and then let's look at problem number 4. Okay, so problem number 4 is the Stokes theorem. Stokes theorem question right here. So let's see how can we deal with this one here. Okay, this is Stokes theorem exercise. Alright, so Stokes theorem is asking to find the work done by the vector field around the curve C. Okay, so this is the curve C in which the plane z equal to 2 meets the cone. So this is z equal to 2, cut the cone, so you end up with this curve C, right? Yeah. Direction counterclockwise as viewed from above. Okay, so now if you recall from the lecture, so I do have the Stokes theorem formula here. If you recall from the lecture, one of the thing that you got to be careful is the orientation of the curve C and the surface S needs to be compatible, right? Yeah. So compatible basically means if given the orientation of C, then you need to choose the uninormal vector n hat for the S, okay, properly, such that they satisfy this right-hand rule. So in this case here, what will be basically, any surface, there are 2 directions. So first of all, if it asks you to evaluate this this line integral, basically you're asking this line integral over C and F dr, right, to calculate. This is basically the total amount of work that is done, right? Yeah, or this side here. So you're not going to evaluate this. If it's asked to Stokes, you're going to evaluate this side here, right, to get the results here. So C, the relationship of C and S is C is the boundary for this surface S. And as we learned in the class, for the same curve C, you have infinite number of surfaces. You can have a surface like this that's share the same boundary as this cone, right? Yeah. You can even have this as simple as just this is the surface, this disk. Okay? So you can choose any surfaces to evaluate this surface integral over here. Okay? Yeah. Now in this question here, I'll choose I'll choose not a very easy surface, but you'll see just practice. When you practice, then I will see can you choose this surface. Okay, so what am I going to choose? I'm going to choose this is a surface, this cone here. Okay, yeah, but in your exercise you can try to choose this guy here. Okay, this surface. Okay, yeah. So so I'm going to choose this surface S. Okay, is the cone. Okay, yeah. So this is the cone, z equal to x squared plus y squared. Okay. Now I'm going to use this divergence theorem. Stokes theorem in here. Okay. So let's take a look at the Stokes theorem. How do we make use of that. Okay, inside this surface integral, okay, we need to calculate this cross product, and we need to get this n hat dA, right? N hat dA. This is okay. You already got the vector field F. We can easily calculate the cross product. Now the n hat, as I mentioned, n hat needs to be chosen properly such that it satisfies this right-hand rule, right? Yeah. So if I'm coming back here, okay, this is the n hat direction, but why, right? What you can do is, as in the class, you can use right-hand rule. So you can use the thumb in this direction, and then your index finger, okay, tangent to this cone, and the middle finger pointing direction is in hat. Okay, so not very good drawing, but you see what I'm saying, right? Or there's another way you can get is this. So what you can do is pick a small location on the surface S. Okay, so you draw a circulation. Basically, consider it a small circulation in here at that around that point. Okay, so if I draw a circulation here, so let's look at this. If I actually draw this way, that will be properly the right circulation. Because why? Use your right hand rule, right? Curve your finger in this direction. So you see that flow direction right here is in the same flow direction as this curve C. Okay, yeah. So that's fine. That's compatible. At the same time, you see here the right hand rule. Then you get your n. You get your n hat, right, pointing to that direction. Right hand. Curve your finger. The thumb is the direction of n hat. Okay. So then that basically tells you this n hat is in an upward direction. Right? It's not this direction. It's the upward direction. Okay. If it is upward direction, you look at this. This is S, surface S. This is a surface S, right? This surface S, and that surface S is Z equal to f of x, y. Okay, and that's basically an explicit surface. If it's an explicit surface, then you are going to choose, okay, the last one here, right, for this dA, and n hat your direction. And we just figured out n hat has to be upward direction, so we use the positive sign out here. Okay, so then the n hat dA, okay, is negative fx, negative fy, and then 1, right, and dx dy. Okay, so you need the partial derivative. So partial derivative of this with respect to x, okay, and you get, okay, 1/2 2x over x squared plus y squared. Okay, so practice this partial derivative, and then you get this partial f over partial y. Similarly, you get this. Okay, so seems to be complicated, but there will be lots of simplifications here. So this is n hat dA, right? And we need to calculate del cross f. And this guy here is essentially the determinant of a 3×3 matrix for cross product. This is a curl, right? Yeah. X squared minus y squared. This is vector field. Okay. Yeah. So you also have the formula for cross product in the formula sheets, and this is the guide here, right? So you can calculate that easily. You get -4, -2x, and 1. Okay, so that's del cross f. Now we're ready to plug this into here, and this guy into here, right? So then what do we get? So that surface integral S del cross f n dot n hat dA, okay, is equal to, okay, so -4, -2x, 1 dot this whole chunk. So 2 get cancelled, negative, okay, negative x over this guy, negative y over that square root 1 dx dy. Okay, so calculate this dot product here, right? The dot product. So we get s. Okay, 4x over x squared plus y squared plus 2xy over x squared plus y squared, then plus 1 dx dy. Okay, so right from here it looks like impossible to do this integral, but remember, how do I find xy limits? Let's look at this. Xy limit is the shadow of the s in the xy plane. So the shadow of the s in the xy plane is actually a circle, right? So we need to consider, instead of Cartesian coordinates, we can consider polar. So the shadow right here is a circle. What's that circle? It's this x squared plus y squared equal to 4, right? Yeah. So we can use polar coordinates. So use the polar coordinates. X is r cos, y is r sine. So plug it in here, so that becomes r squared, and the square root is r. Okay. So 4x is 4 times r cos theta over r. 2 times r cosine theta, r sine theta. So r squared cosine theta sine theta over r. Okay? Yeah. Plus 1. So dx dy becomes r dr d theta. R limits 0 to 2 pi, 0 to 2 pi cos theta. Okay? Yeah. So this looks much cleaner, right, to deal with. So the integral, this r cancel. Okay, so this is 4 cosine theta for the first integral. Okay, yeah, there's still r over there, right? Yeah, still r. So, but it's much simpler. So this guy times this. Yeah, this guy cancel 1r. So 2 cosine theta sine theta is sine 2 theta. Okay, so I think I have it in the formula sheets. So the formula sheets include this trig identity right here. Okay. Okay, so multiply the r, integrate everything. It's not bad. So you get a 4 pi here. Okay. Yeah. Okay, so that's a pretty long video here. I mean, what you can see is it's not that tricky, right? You need to understand the definition behind each one of the formula and particularly the meaning of Stokes theorem and divergence theorem, right? The Stokes theorem, the tricky part is the orientation between the C and S, and also the n hat, right? But ultimately it boils down to a surface integral on this side here, right? Yeah. Okay. If you have any questions, let me know, right? As I said, unfortunately, I cannot be here during the final exam. But my suggestion for preparation is to start with assignments and read through this lecture notes if you've got time. Okay, there are tons of examples in lecture. There are also additional exercise posted on the Connect. So you have lots of basically examples, you know, additional questions to practice. Okay. Yeah. Good luck.